Hello, my dear students. This is Dr. Mohka, and today we'll be explaining physical quantities and measurements. This is the lesson content which we need to cover for the core and for the supplement. The measurements we need to learn for today is we need to measure time in seconds, we need to measure length in centimeters or meters, and we need to measure volume in milliliters or centimeter cube. To measure time, for example, we have to use a stopwatch. First of all, to find the difference, I have to make sure that they are all in seconds before I move on. So looking at the stopwatch here, we have minutes, seconds, and 1/100th of second. The seconds and 1/100th are already done for me, so that's 22.10 seconds. As for the minute, I'll convert it to seconds. So I have 1 minute, so that's basically 60 seconds. And I'll add them. So this will give me 82.10 seconds. Same thing applies to my end of the experiment time. I have 46.5 seconds already done for me. I'll convert the 3 minutes to seconds by multiplying 3 times 60, which is 180, and I'll add that to my 46.5 seconds. To find the difference in time, I'll do the end time minus the start time. So let's check the answer together. End time, which gave me 226.5 seconds, minus start time, which gave me 82.1 seconds, is equal to 144.4 seconds. Let's do another example. A digital stop clock measures time in minutes and seconds. The stop clock reads 00.50 when it started, and it reads 02.10 when it stopped. Let's convert those two values to seconds. So it started at 00.50, so that's 50 seconds. So my start is 50 seconds. And it ends at 2:10, so that's 2 minutes and 10 seconds. So 2 minutes, that's 2 times 60, and 10 seconds, so plus 10, so that's 130 seconds. Subtract them from each other. 130 minus 50 is 80 seconds. Putting this into minutes and seconds, 1 minute is 60. So 1 minute. And how much do I have from the 80? 80 minus 60 is 20 seconds. So my answer is going to be B. Next, measuring time. Sometimes you use a pendulum to measure time. The problem with a pendulum is it goes and comes very fast, so I can't accurately measure the time that it does this complete oscillation. So let's start by first knowing two things. Number one, the pendulum has a wire connected to a bob, which goes and comes. Second of all, for one complete oscillation, it has to return to the starting point. So if it starts at A, it has to go all the way to the end and come back to A for one full oscillation. What if it starts in the middle? It goes all the way to B and it just goes back to A. Is that a complete oscillation? No. It has to go all the way to the end. It has to go all the way to the extreme ends and go back to the starting point. That's one full oscillation. So, as we said, this happens really, really fast. So what do? If the time is too small when using a pendulum, first of all, I'll take a couple of oscillations to go and come. So for example, I'll take 20 periods of oscillations. And then I will calculate the time using my stopwatch for those 20 oscillations. Let's say it took 40 seconds. And then I'll get the total time by dividing it with the number of oscillations. So since I want to calculate the time, I'll put the time up and the number of oscillations down. So that's going to be 40 by 20, which is 2 seconds per oscillation. Let's take an example. A student measures the time for 20 oscillations of a pendulum and records it at 40.2 seconds. Calculate the period of one oscillation. Period means time. So what am I calculating? The time or the oscillation? The time. So I'll put the time up, 40.2, and the number of oscillations down, which is 20 oscillations. Suggest one way to reduce the percentage uncertainty in this measurement. The best way to reduce the uncertainty is to calculate more oscillations. Let's check the answers together. So, the period for one oscillation t gave me 2.01 seconds. And to reduce the percentage of uncertainty in this measurement, I will time more oscillations. Another example is asking a student sets up a pendulum but notices inconsistent timing results. What are two possible sources of error in this setup, and suggest improvements to reduce these errors? Errors could be reaction time. Reaction time means that when I started my stopwatch, I might have done it a bit slower than usual, or I've done it before the oscillations even start. So this is called reaction time, how I'm reacting to a certain experiment or a process. Second of all, maybe the pendulum is not just going and coming in one plane, it's actually going in circles or round. So pendulum is not swinging in a single plane. Maybe it's going to a high amplitude, a large amplitude, which is affecting the time for me to know how far it's going to go and come back. How can I improve this? I'll use a fiducial marker, which means that I will mark the starting and ending point. I'll time more oscillations, and I can just use an electronic timing or video analysis to be very precise with where it started, where it ended, and the exact time. Another example is giving us a diagram and says that the diagram shows a pendulum that oscillates between P and Q. Which method is used to find the average period of oscillation for the pendulum? Remember, we said for a complete oscillation, I have to make sure that when it starts from a certain point, it goes all the way to the extreme and comes back to my starting point. Let's see the options we have. Measure the time it takes to swing from P to Q. That's not a full oscillation, so A is not a correct answer. Measure the time it takes to swing from P to Q to P, so that means it goes back again to starting point, times and divide that by 10. Okay, so that's an option. Measure the time it takes to swing from P to Q to P 10 times and measure and multiply that time by 10. Okay. Measure the time it takes to swing from Q to P. No, that's not a full oscillation. Okay, B or C. After the full oscillation, they said we're going to do that 10 times and divide by 10 or multiply by 10. Like we said, we always divide. So we're going to choose B. Next, measuring length. And usually when we measure length, we use a ruler. Now, we have to be very careful that each dash we have on our ruler is equal to 0.1. So if I have something marked here, then this will be, for example, 3.3 centimeters. What if I'm measuring something very small, like a thickness of a paper? What do? Then I need to take many sheets of papers, measure their total thickness, and then divide by the number of sheets that I have to get the thickness of one sheet. How do we do that? Let's take an example. Here we have a closed textbook, which has 270 sheets of paper in the textbook. The total thickness of the sheets is 29 millimeters. Calculate the average thickness of one sheet of paper. Again, read the question. Calculate the average thickness. So I would put the thickness up, which is 29 millimeter, over the number of sheets, which is 270 sheets, to get my answer. And of course, since I calculated my thickness in millimeter, then my final answer will also be in millimeters. So 29 by 270 is 0.11 millimeters. Here's another example. A student uses a meter rule to measure the length of 6 identical table tennis balls placed between 2 wooden blocks. What's the diameter of one ball? Of course, when I want to measure, I will not measure anything related to the block. I'll measure where the identical table tennis balls start, which is at 38, and stop, which is at 62. Now, the difference between those values, I'll do 62 minus 38, which is 24 centimeters. Now they want us to measure the diameter of one bowl only. I have 6 of them, so 24 divided by 6, which is going to give me 4 centimeters. Next, we have measuring volume. We have 3 kinds of volumes that we can measure. We can measure the volume of a regularly shaped solid, like a rectangular block or a sphere. So for each one of those shapes, they have their specific equation that we can use, which we're going to discuss in a later lesson. For now, let's measure the volume of a rectangular block. The equation to measure the rectangular block's volume is to multiply length times width times height. So if I have the length as 2 centimeters, for example, width is 1 centimeter, and height is 3 centimeters, I'll just do length 2 times 1 times 3, which will give me 6 centimeter cube. Next, I can measure the volume of an irregularly shaped solid, like a toy or an unknown shaped sphere, or any object that has an irregular shape that is a solid. This is a very easy process. First of all, I will not use a ruler. Here I'll use a measuring cylinder. First step, I'll add water to my measuring cylinder and measure or write down the volume of the water before I add the object. Then I will add the object and measure the new volume of the water. And then I'll just subtract the values. So for instance, here it was 50 milliliter, which is by the way the same as 50 centimeter cube. And in the end, it was 65 milliliter, which is the same as 65 centimeter cube. The difference between them will be 15 milliliter or 15 centimeter cube. Last but not least, to measuring volume is to use a measuring cylinder, but make sure to read it at eye level. So I should not go from up or from down, because this will result in parallax error, which will give me an inaccurate reading. Here's an example. A student is asked to find the volume of a small irregularly shaped piece of rock, and we have a balance, a measuring cylinder containing water, and ruler. Remember, we're measuring the volume of small irregularly shaped piece of rock. We said if it's an irregular shape, we do not need a ruler. We do not need a balance because we're not measuring the mass. So they're asking which apparatus must the student use to find the volume of the small piece of rock. We're just going to use a measuring cylinder. Another example is showing different 600-gram masses, identical masses, and a measuring cylinder and a beaker containing water. And they're asking us what to do to determine the total volume of the 6 masses. So as we said, we're going to add water, measure the initial volume of water, and then add the masses, measure the final volume of the water, and then subtract. This question is usually for 3 marks, so we have to make sure that you write the initial steps of adding water and recording it initially, adding the masses and recording the new volume, and subtracting. Here's another example, and the purpose of this example is to know that you are able to read exact measurements from a measuring cylinder. For the first one, we have 1.0 to 1.5, that's where my water is located, and we have 5 increments between 1.0 and 1.5, which means that each dash or each increment is equal to 0.1. So where the water stops is at 1.2. Second measuring cylinder has 2 up to 3 and 5 increments in between, which means that each increment is not with a 0.1 because there are only 5 from 2 till 3. So each increment will be 0.2. How do I get it? I can easily divide the 5 increments by the number I have, which will give me 0.2. So Here it's going to be 2 is it 2.2? Nope, it's 2.4. For the third cylinder, I have 20 to 30. Again, only 5 increments. If I only have 5 increments, then each one will be with 2. See? 2, 4, 6, 8, and then 30. So, where did the water stop? It stopped between 4 and 6, so this will be 25. So, here they're giving us the values and they're asking which readings are correctly recorded. 1.2 is exactly like we got, 2.2 is incorrect, 25 is correct, so we have 1 and 3. Next, we need to know about the scalar and vector quantities. What's the difference between them? Any scalar quantity is just a measurement of the magnitude, which is the size only. However, a vector quantity has the magnitude and the direction. For example, if I tell you I've driven 20 kilometers, then this is a scalar quantity. But if I tell you that I've driven 20 kilometers to the left or east or north, then I also give you the direction, and this is a vector quantity. So examples of scalar quantity include distance, speed, time, mass, energy, and temperature. Examples of vector quantity include force, because you know that force is related to gravity, so that's a direction. Force, weight, velocity, acceleration, momentum, electric field strength, and gravitational field strength. Next, we need to know how to get the resultant of two vectors. We have two ways of doing this, one by calculation and two by graph. Let's start with the calculation using Pythagoras' theorem. If I have two vectors, A and B, to be able to do that, I have to make sure that they are at 90 degrees, as you can see here. So how do I get the resultant vector? To get the resultant vector, I'll square root a squared plus b squared. So square root a squared plus b squared. And this will give me the value of my resultant vector. What if I need to find the angle for the resultant vector from where it started, which is this angle, because usually this is your starting point. So how do I get this angle? I'll just do tan theta, and we have to memorize this, is equal to opposite over adjacent. What do we mean by opposite over adjacent? This is something I'm sure you've taken in math, but let's do this. Check. If I have a right angle triangle, here's my right angle, and I need to, for example, find this angle theta. The face right in front of my angle is called opposite. And the face right in front of my right angle is called the hypotenuse. And the face between my right angle and measured angle is the adjacent. So now that I know what each length is called, if I want to get my angle, I will use tan theta is equal to opposite over adjacent. Let's take an example together to understand it further. Example 1. A box is pulled by two perpendicular forces. Force A, which is 3 newtons to the right, and force B, which is 4 newtons upward. Okay, how do I do that? I can take A as my 3 newton and B as my 4 newton and use my equation R is equal to square root A squared plus B squared to get the answer. And my answer is, of course, in newtons, just like my other two values of forces. What if I want to get the angle? We said tan theta is equal to opposite over adjacent. If you draw these, you're going to find that you're going 3 newtons to the right and then 4 newtons upwards. This is your right angle and this is your angle. So my opposite here is going to be, this is my opposite. So it's going to be 4. So tan theta is going to be equal to 4. And my adjacent is between both angles, so that's 3. So tan theta is 4/3. If I want to just get theta, so on your calculator, you're going to do shift tan, which is going to give you this one, 4/3, which will give you your answer in degrees. And don't forget to put the direction. As you can see, it's going north, east, as you can see from your graph. Okay. Here's another example. A plane is flying 100 meters per second east. So that's this way, east, 100 meters per second. And 60 meters per second north. And this is, of course, a right angle triangle. And I want to get the resultant force, which is this one. Let's label before we actually start solving to make it easier for us. This is my angle theta from my starting point. So this is my opposite. And this is my adjacent. Now let's find our answer. What do I do? To get the resultant, I will do r is equal to square root 60 squared, doesn't matter the order, plus 100 squared. And if I want to get the angle, I'll do theta is equal to shift tan. We said opposite over adjacent, so 60 over 100. Let's see if we got it right. Here we go. So the resultant force is 117 meters per second, and my theta is shift tan 60 over 100, which is 31 degrees, and do not forget the direction. It's going northeast. If you can't remember the directions, this is north, south, east, and west. We went northeast. Okay? All right. So what if they didn't give it to us as numbers, they just showed it to us in a graph? First, I'll choose a scale which fits the page. I'll draw the vectors at right angles like we've done in the previous examples. I'll complete my rectangle to make sure that I know which way is my resultant going. Draw the resultant vector diagonally from the origin. Carefully measure the length using your ruler. And you can use the scale factor to calculate the magnitude if they give you a scale factor like they've done here. And finally, use your protractor to measure the angle. Here's an example. A force acts on an object with 60 newtons to the right. A second force of 100 Newton acts on the same object in the upward direction. Calculate the resultant force acting on the object. So what we've done is we've used our graph paper to draw 60 newtons to the right. We've considered one box to be 10 newtons and 100 newtons up. We're going to either measure it or calculate it, but they asked us to calculate it, so we're going to use the steps we've taken previously. So the resultant will be square root of 60 squared plus 100 squared, which gave 117 Newton. And then we need to get the direction of this one, which is theta. And you already know this is the right angle. This is going to be the opposite in front of our theta. And this is going to be the adjacent between the two angles. So Shift tan opposite over adjacent, 100 over 60, to get 59 degrees. So my final answer will be that I have 117 newtons that are at 59 degrees from the horizontal. And don't forget to mention the direction. So this is northeast. Here's another example. Which vector diagram correctly shows the force Z as the resultant of forces X and Y? Now remember, we have to start from the starting point. So if I started at X, can I have X and Y both going out from the same point? No. Okay, so A and B are going to be incorrect. And C started from X, went on to Y, but Z shows the directions if it's going back. No, the resultant force always starts from the starting point. So my correct answer, as you can see, is D. We started with X, moving on to Y, and the resultant starts from the starting to the ending point. That's how we put the resultant force. Thank you so much for today's lesson, and I'll see you in the next lessons video.